I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask you just bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So sorry I got such a late start today. I probably should set my alarm here so that I don't go too late, you know. Let's see here. I will set it. Oop, not 5. That's probably bad. So if I set it for that should be just good. There we go. All right, so we are now in chapter 7. So this is foundations of quantum mechanics. All right, so again, this is from, this wonderful book here by Debneth and Mikuzinski. I can't say anything today. Let's see here. I guess we could read the quotes at the start of the chapter. That's always fun, right? The tool which serves as an intermediary between theory and practice, between thought and observation, is mathematics. It is mathematics which builds the linking bridges and gives ever more reliable forms. From this it has come about that our entire contemporary culture, inasmuch as it is based on the intellectual penetration and exploitation of nature, has its foundations in mathematics. As Galileo said, one can understand nature only when one has learned the language is mathematics, and these signs are mathematical figures. Without mathematics, the astronomy and physics of today would be impossible. These sciences and their theoretical branches virtually dissolve into mathematics. Quote from David Hilbert. Now a quote from Dirac. The research worker, in his efforts to express the fundamental laws of nature in mathematical form, should strive mainly for mathematical beauty. He should take simplicity into consideration in a subordinate way to beauty. It often happens that the requirement of simplicity and beauty are the same, but where they clash, the later must take precedence. Dirac, whatever that means. All right, so our aim is to discuss the basic concepts and postulates of quantum mechanics in terms of the results of the theory of operators in a Hilbert space. So let's see here. Section 7.2 is on basic concepts of classical mechanics. And I think I should at least briefly go over some of the high points in this section, partly so that we can appreciate what happens with quantum mechanics. So I'll try to briefly go over the high points here as much as I am successful in that. The basic idea so let's talk about section 7.2, which is classical mechanics. So the basic idea of classical mechanics, of course, is that you can write things in terms of energy equations, right? So in particular, you can introduce the Lagrangian, right? And the Lagrangian L is equal to the kinetic energy T minus the potential energy V. It is a function, and this is important, of phase space. In particular, the position and the velocity of, and this sub I is to index over particles, all right? So Lagrangian is a function of position and velocity. Taken together, those are called phase space, all right? And you have the Euler-Lagrange equations, right? Euler-Lagrange equations give you the equation of motion, and those are this. They're ddt of partial L, partial xi dot equals to partial L, partial xi. So those are the so-called Euler-Lagrange equations. These reproduce Newton's second law, as well as other things like the torque equation, right? And they produce equations we don't have a name for in introductory physics because they're general. and these hold for, coordinates. They don't just have to be Cartesian coordinates, right? I've written for Cartesian coordinates, but I would be better to use Q's to indicate generalized coordinates. All right, so he has, oh man, I wish I had more time. He has some beautiful general theoretical discussion in here, but eventually he, well, let me just do some erasing here. Let's use Q's. Okay, so I'll just be brief. Q sub I dot. All right, so like your generalized coordinates, it could be the x coordinate, the y coordinate, the z coordinate for a first particle, and then qi dot could be x1 dot, y dot, z dot for that same. So you could anyway, so generalized coordinates, right? In that context, he defines so this right here, partial L, partial Q j dot, this is equal to pj. This is the jth generalized momentum, right? And likewise, the F sub j, the jth generalized force, is partial L, partial Qj. So in this language, you see that the Lagrange equations become what?
This is Newton's second law.
Exactly. Yeah, exactly. So, but generalized, right? So like, this becomes dpj dt is equal to fj, which is exactly, that's Newton's second law, the momentum version of it. So just a couple examples before I go too far away from this. Example 1, you could have Lagrangian is 1/2 m x dot squared plus y dot squared, right? Example 2, you could have L is 1/2 m r dot squared plus r squared theta dot squared, right?
And dots are representing derivatives, right?
Yeah, dots are time derivatives. This was Newton's notation for the derivative, and it lives on in physics. Leibniz beat Newton in the notational calculus war, right? Because it's all dy dx all the time in calculus. But I do like to throw some dots into the mix because it's way easier to write. But yeah, time derivatives. Now, so here, notice like partial L, partial x dot is just mx dot, right? Partial L, partial y dot is my dot. So you might recognize these as just the usual px and py. These are just linear momenta. In contrast, though, if we look at partial L, partial r dot, we get mr dot, right? And if we look at partial L, partial theta dot, we get mr squared theta dot. So this again is just radial momentum. It's a linear. R is a linear coordinate, so it gets a linear momentum, if you will. So that's the velocity in the r direction, right? Whereas this, you might recognize as L equals mr squared omega, or I omega, right? It's angular momentum. So the Lagrangian perspective naturally folds in concepts that we have separated in the regular classical mechanics class, and it gives us a general definition for like momentum as being the partial derivative of the Lagrangian with respect to the jth coordinate derivative. The book says that, momentum and position, these are so-called conjugate variables. All right, so, and you should understand that when we take the Euler-Lagrange equations, these are derived from an action principle, right? And that's all happening on phase space. Phase space is this interesting contraption where we're treating qi and qi dot as independent variables. So there's some interesting mathematics to explore there, right? Actually, it's something called a jet space. ultimately leads you to look at something called the jet space. Not at this level, perhaps, but you can look at basically you just look at a higher dimensional space where you add dimensions and corresponding to the variables you want to make independent. So you just for a particle in 3 dimensions, phase space is a 6-dimensional space, right? And you can look at curves in that 6-dimensional space. Some of those will correspond to the actual motion of a physical object, right? For those ones, the first 3 dimensions of the 6-dimensional space and the last 3 dimensions of the 6-dimensional space, they have to be related in a very specific way, namely that the qi dot has to actually be qi dot. But that whole story is an interesting story, but not one for here. Anyway, so that leads us to define the Hamiltonian. The Hamiltonian is a function of momentum and position. So you trade out the q. There's no dot. There's no qi dots. All right. In particular, this is the formula he gives for it: pj qj dot minus L. Now, let's see here. Let's get to it. So let's see here. He derives a little bit later that this is equal to T plus V. All right, so the Hamiltonian is kinetic energy plus potential energy. All right, and let's see here. So, I mean, the most elementary example of this exchange, like think about this. You could write kinetic energy, right? 1/2. Yeah, I'll come back and get you a second here. 1/2 mx dot squared, right? One half m x dot squared, right? We good? You got me, right? So that would be that would be how I would write it for a Lagrangian formalism, right? How would I write kinetic energy in the Hamiltonian formalism? Instead, I would trade this for a px squared over 2m. See, because px is mx dot, right? That's the relation between the x momentum and the x velocity. So you can rewrite kinetic energy in terms of momentum. So, in the world of the Hamiltonian, if you want to derive, so-called Hamilton's equations from the Hamiltonian, you'd be working in a space where the momentum and the position are taken to be independent, at least in the abstract. Yeah.
Isn't the Hamiltonian was equal to the total energy? Doesn't that only hold with like certain conditions, like when the Lagrangian isn't
Isn't the Hamiltonian only equal to the total energy given certain conditions? This is true. This is true. And I don't want to get into all that.
Yeah.
But you're right. I mean, we have to get into the whole, there's a much larger discussion about constraints and anholonomic and holonomic, and this is why classical mechanics is a course. Yeah. And I am sadly unprepared to I'm not ready to get into that nuance here, but he does. He does have this equation. This is on page proof by book, page 359. Anyway, okay, great. Now, okay, so in terms of, let's look at this here. So what do the Lagrange equations become? What do they translate into here? If we just directly translate them, you have ddt of what? Before we had partial L partial Q dot, right? That apparently is Pj, right? Equals to what? partial L, partial Q, QJ, just partial QJ, right? But remember, let me just do a little derivation right here. If we believe, that's partial QJ of what? Of the sum, right? Over J, I mean, I probably use sum over I, okay? Sum over I of P I Q I dot minus L. Oh, my bad. I'm so sorry. I'm trying to change this to an H and I am failing. Try this. Let me try it again. 1 minute. I solve for L. I'm going to solve this over here. Sorry, Audric, you probably can see both at the moment.
Yeah.
But the camera can't. No, you're fine, Jacob. I need to look. I'm trying to straddle the fence here because I want both. So I'm trying to solve this over here for L, right? So if I solve that for L, I've got what? L is equal to, it's the sum, right? Over I, let's say, of Pi Qi dot plus H, right? So, okay, and then so the thing is, I want to say this piece is 0. All right, so this piece is 0 because, again, we're treating Q and Qi dot as if they're independent. And we're also treating the P and the Q as if they're independent. So, admittedly, there's some funny business going on here. It drove me nuts as an undergraduate. It still drives me nuts. If I ever was to teach this properly, I would have some reckoning to do. But anyway, there you go. I believe these are Hamilton's equations. I could be wrong. It's been a minute since I've looked up Hamilton's equations. He's got to have these in here somewhere, yeah? Does he not have Hamilton's equations?
Is it the 358?
7.32, 358? Yes. Okay, there we go. Thank you. Yeah. So this, what I just derived right here is, wait a minute. No, that's not it either. Oh, maybe 733A? No, that's not it either. 733B?
Oh, it says, yeah, 733B says Hamilton's canonical equations of the books.
Oh, and I've missed a minus somewhere, right? Oh, dummy. There's a minus here, right? Duh.
Yes.
That's a minus. This is a minus. This is equation 7.33b in the book, if you're keeping score there. And then he has a number of other partial derivatives that relate the Lagrangian to the Hamiltonian, which I won't write up here. I just wanted to show you. This is the analog of Newton's second law in the Hamiltonian formalism. All right. So, to this day, you got two choices when you do theoretical physics. You can form things in a Hamiltonian formalism, or you can form things in a Lagrangian formalism, and you know, they're connected and they're different, and I think we need both. So it seems to.
And just to be clear, the Lagrangian is looking for the difference between the energies, whereas the Hamiltonian is looking for the sum.
That's what it is in a certain context. Yeah, I mean there are terms and conditions that come with the Hamiltonian just being the kinetic energy plus the potential energy, but oftentimes that's what it is.
Quantum mechanics, I think it always is that because the open surfaces.
Oh yes, in quantum mechanics, the Hamiltonian operator is always the kinetic energy plus the potential energy. Yeah. So now I do think it's important to see some of this stuff because yeah, you can turn over here. To understand the genesis of quantum mechanics, you have to understand that the people who wrote quantum mechanics down were deeply schooled in classical mechanics. They understood classical mechanics far more deeply than we do today. And so when they wrote down quantum mechanics, it was a natural extension of the theoretical physics that they already knew for wave motion, which was born.
See, the classical mechanics that we solved, is it, or was it solved back in the early 1900s?
Was classical mechanics solved? I don't know. What do you mean by that?
Like, for example, like, you know, the preeminent question of the time, Herbert's orbit, the three-body problem, you know,
So,
things that, like, Newton's mode.
I mean, well, there certainly are unsolved problems in classical mechanics to this day, but
But is that because of inherent,
it's not a, yeah, not, it wouldn't, I wouldn't say it was a failing of the theory. It's just those are hard problems, you know. Classical mechanics was successful in predicting, you know, paired with Newton's universal law of gravitation, you know, with predicting the vast bulk of solar, like orbital motions of bodies and things, you know, up to just a few little, you know, missing pieces here and there that turned out to be general relativity, like the precession of the perihelion of Mercury and some things like that. Of course, you know, everything that has to do with time dilation was completely missed by classical mechanics, but understandably so, you know.
so we don't teach classical mechanics so not because it's like solved anymore, but just because it's not the only thing to teach at this point.
Oh, no, no, we still teach classical mechanics. Classical mechanics is still classical mechanics is to the physics major as real analysis is to the math major.
I'm not saying that. I'm just saying like back when people were discovering quantum mechanics, all the biggest ideas were classical mechanics.
Oh, right.
So you spent the bulk of your time learning classical mechanics.
Yes, exactly.
Now we have classical and quantum, so you split your time.
Oh, this is very true, yeah. The classical was the only game in town when quantum mechanics came on the scene, for sure. But yeah, now our interests are certainly bifurcated. So this is an important discussion. Poisson brackets in mechanics. He's like, if you have any canonical function, if you have a function of, let's say, pi and qi and t, so just some function, so-called canonical function, then the equations of motion for such a function can be derived from the Hamiltonian as follows. So df dt is equal to some I equals 1 to 3n of partial f partial qi dot plus partial f partial pi dot, and then plus partial f partial t, which you can rewrite in terms of the Hamiltonian, because this right here is partial h partial pi, and this right here is partial h partial qi. But I need a minus when I do that, right? Minus. So, by the way, what I'm writing right now, these are Hamilton's equations. Yeah, these are Hamilton's equations. Both of these together, Hamilton's equations. I'm pretty sure that's what I called them when I was an undergraduate anyway. Now, the interesting thing then is, let's see here. The df dt, oh man, I hate that he straddles a page with this calculation. It's equal to the Poisson bracket of f and h plus partial f partial t. Now what is the Poisson bracket? This right here, good grief. The Poisson bracket of f with h is literally so annoying. As he has it currently set up, sum I equals 1 to 3n. Partial f, partial q, I, partial h, partial p, I, minus partial f, partial pi, partial h, partial qi, close big parentheses around these guys, and then plus partial f, partial t. That's not the Poisson bracket, of course, but let me not put that in there. I don't believe the partial f, partial t is part of the Poisson bracket, right? Yeah. No, it is not. So what this Poisson bracket is doing is it's this funny algebraic thing that's like weaving the equations of motion into this bracket, you know, like it's got the Hamilton equations all wrapped up in it in some sense. And so let's see here. And so he rattles off some Poisson brackets of, you know, some various things that you can calculate, and I should just write those on here. Because in some sense these Poisson brackets become commutator brackets as we transition to quantum mechanics in some sense. Oh, there it is. So if the canonical function does not explicitly depend on time, we just have df dt is equal to the Poisson bracket of f and h, right? So this is you know, given partial f, partial t is 0, right? And so some nice examples of this, rattle some off here. The Poisson bracket of qi with pj is Kronecker delta ij. The Poisson bracket of like qi with itself, or qi with qj, or pi with pj, these are 0. The Poisson bracket of li with lj is equal to lk, assuming that I, j, k are in cyclic order. What else can I tell you? The Poisson bracket of li with L squared is equal to 0, where L squared is equal to like Lx squared plus Ly squared plus Lz squared. I see we're engaging in a mixture of x, y, z versus ij notation here. Feels like home. It's good to be back in physics again. Let's see here. Yeah, that's good. It's a good synopsis of things here. I guess we could let's work out one of these, because I think I asked you guys to work out some Poisson brackets in your homework. Let's see here. Let's try the one dimension. You know, let's look at what's the Lagrangian. Excuse me, the Hamiltonian for just one particle, right? It's what, 1/2 m. Well, excuse me, 1 over 2m rather, right? P squared. That would be it. And so what happens if I try to calculate the QP? This is the simplest thing I could possibly think of in here, right? Okay, first of all, so I'm taking f. I'm supposed to calculate, what? Hey. Oh, I'm confused. How does he calculate that? So does he start out with h being the Hamiltonian, then he lets it be a variable? Well, how are we even calculating the Poisson bracket of anything with anything else unless it's the Hamilton? I mean, I don't get it. You know what I'm saying? Like, where's his definition of Poisson bracket?
Yeah, the Poisson bracket of two functions. Okay.
Yeah, his definition is
Oh, so he's not.
It is just that sum that makes
So he's not thinking H has to be the Hamiltonian. This is his definition for arbitrary H. All right, fine. Fine, fine, fine.
He says the fh is called the Poisson bracket of two functions f and h. If the canonical function f is not explicitly dependent on time, then we can also define it as the derivative of f.
Right.
T is equal to
So you're fine. So here, there's no no sum. I just have one. I'm just doing one-dimensional. You know, so it's just this is all this becomes is partial. Let's see here. Let me just write it symbolically. Partial f, partial q, partial h, partial p, minus partial f, partial p, partial h, partial q. Yeah.
Why does he have 30 in as the top?
Oh, because he's enumerating them by number of particles. So like, there's n particles. You have 3n coordinates. Three dimensions. Yeah.
Okay.
Yeah, he's doing that. All right. So all right. My f here is what? F equals to q. My h equals to p. Right. If I understand his definition. So this is, I think this might be irrelevant. All right, so then this is what? Partial h, partial p, so this is 1. And then minus 0, so the answer is 1. All right, great. Not especially exciting, but I am confused. Oh, okay. No, I'm still confused. But anyway, let's go on. My confusion need not be your confusion, so. Oh, I'm sorry, Audric. I never moved you back over here.
Oh, you're fine. I was following along with the book.
Cool. This is what I wrote. Or did you see you saw the purple part, didn't you? That was in the over here?
Yeah.
Yeah, okay.
I was following along. I figured that you were just showing us the derivation.
Yeah, I was trying to anyway. All right, so now finally we made it. Section 3.7.3 let's see here, basic concepts and postulates of quantum mechanics. And so he gives us some kind of background into problems which led to quantum mechanics, namely, failure to explain black body radiation. I think the photoelectric effect has also to do with this story. Let me read this here. He said, also, the failure of classical concepts when applied to the motion of electrons appeared most clearly in connection with the hydrogen atom. According to Rutherford, classical model, an atom can be considered a negatively charged electron orbiting around a relatively massive positively charged nucleus. So here's the picture, right? You've got an electron orbiting, right? And you've got this nucleus proton, basically, right? And so it's orbiting. What's the problem with it?
Why doesn't it crash in?
Yeah, why doesn't it crash? Now, why should it crash in?
Proton's way heavier than an electron.
No, but I mean, the moon doesn't crash into the Earth, right?
Yeah, but it also, you have also the electromagnetic field working against you.
Right. That's the thing, is the electromagnetic field. There's something we learn about electromagnetism if you keep going, and it's this. If you have a charged particle which is accelerating, it radiates. Bremsstrahlung. Bremsstrahlung, I think that's an example of it, yeah. But yeah, accelerated charges radiate. So an electron going around the nucleus is definitely accelerating, therefore it should be radiating. It should be losing energy by electromagnetic radiation, and yet it doesn't. So this was the question that my modern physics professor began our semester with. He explained this in great detail, and he said, so why doesn't the electron, why didn't the electron crash into the nucleus? And we were like, we wanted him to explain, and eventually, basically quantum mechanics says that it just doesn't, which is a deeply unsatisfying answer. But that's essentially the answer that quantum mechanics eventually gives, is that the energy levels that can be occupied by matter are discrete, and there's a lowest energy level, and it can't go below that. That's why it can't get to a lower energy. There's no lower energy for it to radiate energy to, in order to get to that lower energy level. That is, roughly speaking, how the paradox of Rutherford's atom is answered by quantum mechanics, or not answered, depending on your perspective. You remember doing that? Yeah. Let's see here. And he's got some numbers here, He said that the attractive potential would cause the electron to orbit around the nucleus, and the orbiting electron constitutes a rapidly accelerating charge, blah, 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 blah. The accelerated electron would continuously radiate energy, and in a matter of 10 to the minus 10 seconds, the electron should coalesce with the nucleus, causing the atom to collapse. Whoa. So, anyway, thus the Rutherford classical atomic model has two important qualitative weaknesses. Number one, the atom should be very unstable. Number two, it should radiate energy over a continuous range of frequency. Both of these results are totally contradicted by experiments, right? So the original problem of quantum mechanics was to investigate the stability of atoms and molecules, as well as to explain the discrete frequency spectra of the emitted radiation by excited atoms. The remarkable success in prediction of observed atomic and molecular spectra is one of the major triumphs of quantum mechanics. All right, so now he's going to tell us some postulates of quantum mechanics. All right, so as mentioned in previous sections, that classical mechanics identifies the state of a physical system with certain values of observables, right? Position or momentum, for example. On the other hand, quantum mechanics also makes a clear distinction between states and observables. So we begin with the first postulate concerning the state of a quantum system. If you don't mind, I'm just going to read this, because if I wrote it down, it would take me forever. Every possible state of a given system in a quantum every possible state of a given system in quantum mechanics corresponds to a separable Hilbert space over the complex number field. Whoa.
So free particles.
And that sentence feels wrong to me.
Yeah, with free particles.
I think every possible state of a given quantum mechanics corresponds to a state. Excuse me, corresponds to a vector in a separable Hilbert space. All right, anyway, maybe that sentence is somewhat, the next sentence I think makes clear what I'm worried about. A state of the system is represented by a non-zero vector in the space, and every non-zero scalar multiple of the state vector represents the same state. Conversely, every non-zero vector in the Hilbert space and its non-zero scalar multiples represent the same physical state of the system. The particular state vector to which the state of the system corresponds at times t is denoted psi. I'll write something. Here's the wave function, psi of x comma t. All right. In the sense that almost all information about the system at time t can be obtained from the vector psi of xt. He says, usually the state vector is denoted by little psi of x in the Dirac notation, and in general, any state vector psi of x is written as follows. Psi of x is equal to bracket x with psi. All right. and its complex conjugate is equal to psi with x. All right. He is not explaining the difference between the capital psi and the lowercase psi, is he? This is kind of a squirrely move right there. All right, anyway. The postulate makes several assertions. First of all, physical properties of a given system are unchanged if it's multiplied by a non-zero scalar. We can remove this arbitrariness by imposing a normalization condition. All right, so let's do that. So usually we assume what? We assume that the integral of the conjugate of psi and psi of x dx is equal to 1, right? Which in abbreviated form is equivalent to writing bracket psi is 1, right? All right, so he says, for any two-state vectors, phi and psi, the complex number phi psi represents the inner product into space and is given as follows. All right, so let me write that out. So we've got the bracket of phi with psi is equal to the integral over phi bar of x with psi of x dx. And, oh, interesting. So that's equal to the integral over, so you can rewrite that phi with psi, no, phi with x. Oh man, phi x like that, or x, no, yeah, x phi like that. Interesting. Oh, he was already doing that back here, wasn't he? Yeah. So that's reminiscent of the distribution notation, I think. I'm trying to remember. How did we do?
I remember there was a mentioning of something like projection operators where this came up.
Last time we were talking about distributions, we had like f of phi was equal to what? What was it? I know it was like, I'm going all the way back to chapter 6 here for a second.
F was equal to integral f of phi.
Integral f. But he also uses the this notation, right?
Yeah.
Like you said, if it's a
that equals f phi, integral f phi.
provided it's a regular distribution, right?
Yeah.
So the pattern isn't quite the same here, is it? Because he puts the x, he's putting the x first and the psi second, right? See the pattern? I mean, f goes first, phi goes second. Over here, x goes, the first is, the last is the first, and the first is the last. I mean, it's not quite the same pattern. Just saying. That is not a deep comment. Just me musing. All right, so let's see here. Go on. Let me get back to chapter 7. If I can. Come on. All right. He says if you combine all this together, we get that the inner product of phi with psi is equal to the conjugate of the psi with phi. All right? Do you guys see that?
Yeah.
Okay. So because you can flip them, and the conjugate flip. Yeah. Okay.
I mean, that's essentially just like writing it like if conjugate is equal to the.
Right. Yeah. And let's see. We also have this notation, or this is equal to 0, means that the state phi and the state psi are orthogonal. All right, great. Now we're getting somewhere. A set of state vectors is orthonormal. So we can talk about a set of state vectors. So like you've got psi 1, psi 2, da 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 da, you know, orthonormal. Means that if we have, you know, psi I with psi j, what do we get? Kronecker delta ij, right? And in this, and he says an arbitrary vector psi in the state space can be expressed as a sum of a complete set of orthonormal vectors. So if you have an arbitrary state psi, you can write it as a sum I, you know, sum over I of ci psi I, right? And you can calculate what the coefficients have to be for that sum by, you know, taking the inner product, right? Let's see here. He says, obviously this postulate implies the principle of superposition. The number of elements in an orthonormal set of state vectors is called the dimension of the state space. If the dimension is finite, it's a finite series. On the other hand, if the dimension is infinite, it's an infinite series, and hence the question of convergence will arise. Second, postulate 1 asserts that all can possibly be known about the state of a quantum system at time t can be obtained from its state vector psi of xt. On the contrary, in classical mechanics, the state of a system t is completely described if and only if the state variables q of t and p of t are given as definite real numbers. However, the x in psi of xt does not depend in any way on the time variable t. All right. And he's going on to describe some more things here. The third assertion in postulate 1 is that the functional dependence of psi on t is essentially different from the dependence on x. Indeed, as a Hilbert space vector, psi of xt is a function of x alone, and t serves as a parameter. More precisely, psi of xt1 and psi of xt2 are to be considered two different vectors in the space. That is, two different functions of x, which specify the state of system at two different times, t1 and t2. So the state vector psi of xt is often referred to as the state function or the wave function of the quantum system. We write that down. So if we have psi of xt1 and psi of xt2, these are thought of as different, what does he say? They're thought of different functions of x. They're two different vectors in the space, he says, though. Two different vectors in the space. Now, of course, this CI we can calculate, like, you know, may take a second to do something that's comforting in this sea of meaningless words that we're currently wading through.
This is all comforting to me.
Oh, it is? Okay, good. Well, good. Yeah. Okay, so if we do psi j with psi like this, right? Then we have, you know, I guess we need to use some linearity here. Sum over I of like ci. Well, the thing is, when I act by this, fine. This gives me, I mean, there's some things you have to assume here, right? First of all, that this operation is linear, you know. Well, let me just say sum over I, right? It's linear. You can pull the scalar out, right? No conjugate yet. And so you get sum over I, ci Kronecker delta ji, which of course just gives us cj. So, oh, sorry. So, all of this to say, this is assuming, of course, that we have the structure of an inner product here, right? Like, in order for this calculation to make sense, then this, you know, bracket notation I got to be able to pull scalars out without a conjugate in the front. I have to have additivity, you know, and then with all these things said, then we can learn that this is really, you know, it is exactly, you know, psi I acting on psi, I guess, at the moment, you know. Which gives you the kind of stupid looking equation. This is equal to the sum over I of bracket psi I with psi bracket psi I. But anyway.
So these, so the ket just has that straight, just because by definition what it's defined as 7.54.
7.54.
The ket is just a state vector, and that 7.54 is just the completeness, is a reflection that every vector can be written as.
Yeah, the
complete orthogonals.
right, as Jacob's saying, the ket is a state vector, and that 7.54 is based on the assumption that our orthonormal system is complete. All right, so he says, in classical mechanics, observables are simply dynamical variables such as position, momentum, functions of position and momentum. Of course, you can also talk about angular momentum, energy, blah, 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 blah. The measurement or observation of classical observable is a well-defined physical operation that, when performed on the system, yields a single real number. So the value of it's called the value of the observable. We don't even really think about that, you know. So in the study of classical systems, it's tacitly assumed that the operations of measurement do not significantly disturb their motion. You know, more precisely, any disturbances caused by measurement are negligible. In classical mechanics, there's no real difference between the mathematical representation of an observable and the values of the observable. This leads us to formulate the second postulate of quantum mechanics. To every observable in quantum mechanics, software changes are required. Will you shut up, stupid computer? All right. To every physical observer in quantum mechanics, there corresponds in the Hilbert space, in the Hilbert space, a linear Hermitian operator, A hat, which has a complete set of orthonormal eigenvectors, psi n, with corresponding eigenvalues lambda n, such that A hat of, where'd it go? Psi n is equal to lambda n psi n, right? And conversely, to each such operator in the Hilbert space, there corresponds some physical observable. Oh. And then part B of postulate 2, the only possible values of a physical observable are the various eigenvalues. That part of postulate 2 is ultimately what's going to, you know, solve the Rutherford, to save the Rutherford atom from its inevitable demise. All right. So.
And these are all the real eigenvalues, right? Those were Hermitian operator.
Yeah, maybe he's getting there. He doesn't say that they're real yet. According to this postulate, quantum observable, although he said it's Hermitian, so Hermitian operators have real eigenvalues, so it's there. You could, for pedagogical reasons, say that the eigenvalues are real. Yeah. According to this postulate, a quantum observable is mathematically represented by a linear Hermitian operator on an infinite dimensional separable Hilbert space, and there is one such operator for each quantum observable, such as position, momentum, energy, so on. Such operators in quantum mechanics are called observable operators, and they usually satisfy the rules of the theory of operators in Hilbert space. Usually. This weasel word. Usually. Yeah. All right. Where's your footnote? Tell me when it doesn't happen. So the quantum observables are operators in a Hilbert space. However, an observable in classical mechanics is simply a real function of conjugate variables in Euclidean space, right? So, like, what are the consequences of this postulate? As he says, Hermitian implies real eigenvalues. The second consequence is that the nature of the representation of the eigenvalues seem to suggest that they form a discrete set, which leads to the possibility of certain observable operators being quote-unquote quantized. That's hopeful because we've observed the discreteness in the spectra of the molecules and so forth. But he says the most profound difference between the two rules and operations and the rules for manipulating classical observables is that two classical variables, A and B, always commute, whereas two observable operators do not commute in general, and the commutator of those two operators doesn't have to be 0, right? All right. And he has some philosophy here, I guess I should read it. This is the essential difference between operating first with B and then with A, or first with A and then with B. So in general, the commutator of two observable operators is non-zero. Physically, the non-zero value must be associated with the magnitude of the unavoidable disturbances of the two measurements A and B in different orders. So it is appropriate to mention here that what we mean by a measurement is, from a simple physical point of view, a measurement is simply a well-defined physical operation which, when performed on a physical system, yields a single real number without any error or ambiguity in the sense that it has no experimental uncertainty associated with the number obtained. If A hat and B hat represent measurements of two particular quantum observables, for example, A hat might be in position, B hat might be momentum, then AB minus BA with all the hats is not equal to 0. This means that the measurement in quantum theory is fundamentally different than from that in classical mechanics. Measurement of quantum observables does affect the system and so may be expected to appear explicitly in the theory. In other words, it may not be possible to measure two different observable operators in a system simultaneously, and the measurement of one may change the value of the other. All right. And so now he's, of course, going to bring us to Heisenberg's uncertainty principle, right? Which comes from the fact that, when would it be possible to observe two different observables? Like, here's the thing, is if I have A hat and B hat equals to 0, then this means that there exists simultaneous eigenvectors for these observables. So if you want to simultaneously observe the values of both, they have to be such that the commutator is 0. What's that?
Like if we're talking about like eigenvectors, would they have to only be the case where it's a repeat solution, like they're repeated, like I'm thinking of like actually solving for eigenvalues that it would be a repeated solution, so it'd be like
Oh yeah, yeah, sure. Yeah, if I had like yeah, but what I'm thinking of more here is an example of this in quantum mechanics, which is interesting, of course. Well, first of all, when this is not possible, when it's not equal to 0, it's not possible to simultaneously observe. So, probably the most famous example of that is momentum and position. So if you calculate the commutator of the momentum and the position operator, which I have not yet motivated, all right, it works out to IH bar. I'll try to explain more of that in just a second here. Did I do it backwards? Oh yeah, my bad. I'm supposed to do XP. X hat, P hat, all right. Then this means that I can't simultaneously know the position and the momentum of a quantum state at once. On the other hand, it is true that the square of the angular momentum and, say, for instance, the z component of the angular momentum, this actually works out to 0. So it is possible to observe the square of the total angular momentum as well as the z component of the angular momentum for a, oh man, shut up, you shut up. It is possible to observe both of these at the same time. On the other hand, if you do like Lx and Ly, remember, it's equal to Lz, corresponding to the fact that you cannot simultaneously measure the x and the y components of angular momentum at the same time in quantum mechanics. So the game of understanding a quantum mechanical system is finding a set of observables which are simultaneously diagonalizable. And of course, the most important thing of